Is active galactic nuclei. Okay. Again, I don't have a mouse though, so all right, let me just nope, that's not gonna work. Okay. I don't know how to get it out of play mode on this laptop. It's not the same as what you would do.
Okay.
Yeah, escape isn't
So this
working.
one doesn't.
I think because I'm more in the Zoom than in
Okay,
this. Okay.
still
Okay, now I can
missing.
maybe, there we go. Okay. All right. So okay, let's oh, I have to reshare though. Yeah. Okay.
Yeah.
All righty.
Okay.
I'm just
Then close this window. Go
Yeah, sorry.
go to mode.
Yeah.
Hide floating. Yeah. And then
Okay.
play.
Okay. And then yes, I'll leave this over here and that should do it.
Play.
Okay. All right. We're back. Okay, so active galactic nuclei, right? You have a supermassive black hole at the center. You have, according to the standard thin disk model, you have this thin accretion disk. You have the hot corona that is in the region closest to the supermassive black hole and emits X-rays that vary on a variety of timescales. And then in some cases, you have these jets. And so, right, this is the standard thin disk model, right? Which says you have an optically thick but geometrically thin disk. But lately, there have been both simulations and observations that suggest that there may be problems with this thin disk model. So first, there have been a lot of observational campaigns that have showed that maybe the radial extent of an AGN disk is larger than what you expect from the standard thin disk model. Also, there's been both observational and simulations that have showed that maybe you can get these flaring accretion disks. So the standard thin disk model says you have a constant thin height of your disk as you move out in radius, but actually there's been some evidence that maybe your height can increase as you move out in radius in some reasons. And then also you can get a puffed up accretion disk, maybe from convection. And then finally, there's been both observational and simulation-based evidence that you get some variability in these disks that are on timescales shorter than the thermal timescale predicted by the thin disk model. So what I have been working on is trying to develop a new model based on observations and simulations that goes beyond this standard thin disk model. And the tool that I've been using for my thesis research is reverberation mapping, and I'll talk more about that. But I think we can use reverberation mapping and sophisticated new techniques to do reverberation mapping to learn about, so what is the physical origin of variability in UV optical light curves emitted by the disk to kind of probe why you're getting these fluctuations. I think we can use reverberation mapping to learn about the vertical profile of the disk. So do you have flared disks? Do you have puffed up disks? Are they thin? Are they thick? And then also we can learn about how these the vertical profile and the variability change as a function of AGN parameters. So first I use your traditional disk continuum reverberation mapping. And how this works is you have X-rays emitted from the corona that have some variability on a variety of timescales. And these X-rays, some of them just come straight towards us and we observe them. But some of them move outwards along the disk where they're absorbed by the disk and then re-emitted based on the local black body temperature of the disk. So that means we get some light curves in UV and some light curves in optical. And these light curves, because it takes light time to travel to these regions of the disk, they have a lag in them. So you see the variability first in your X-ray light curve, then in your UV light curves, then in your optical light curves. And so I'm going to show you some actual light curves. So these are light curves from the AGN Feral 9 taken with Swift and LCO. And in the top, you can see the X-ray light curve. And then I also show a B-band light curve and a Z-band light curve. And you can see that they vary over a number of frequencies. And you can also actually see by eye this lag. So just short of 450 days, you can see that there's this peak in the X-ray variability. And then if you look in the B-band, it happens slightly later. And if you look in the Z-band, it happens slightly later. And so this is a lag on the order of days. And what I can tell you is the radial temperature profile of the disk, because this emission is based on the temperature. And it can also tell you about the radial extent of the disk, because you know the light travel time, you measure this lag, you can get how far it must be traveling. Okay, but there are some problems with this kind of traditional reverberation mapping, right? Which says that you take your X-ray light curve, you copy and paste it 3 days later, you get your B band, you copy and paste it another day later, you get your Z band, but that's obviously not what's going on in these light curves. So first, right, you can see that there's some smoothing of the variability in the X-ray light curve, and it's not clear yet if that's physical or something else. And then also you can see that there's additional low frequency variability in the Z and B bands. So you can see that this black line kind of sketches out a little bit like a shallow parabola. And this exists in the Z band and the B band, but it's nearly flat in the X-ray band. And so that just means that there must be some intrinsic variability coming from the UV optical region on reasonably short time scales that's producing this variability, and that it's not just all coming from the X-ray. So we want to study this, and I do this with 3D shearing box simulations. So I take a very narrow radial box and I drop it into the inner UV region of the AGN disk. So in my shearing box is 96 96 gas pressure scale heights tall. So it goes from plus minus 48. And that's because the gas pressure scale height is smaller than the radiation pressure scale height. So it's a little more reasonable, but the important part is we want to make sure that we're capturing the photosphere of the disk so that we can look at the flux that's actually leaving the disk. So we have a good enough resolution to resolve magnetorotational instability modes, which is important. And then, yes, so we magnetize these simulations with both a zero net flux magnetic field and a vertical magnetic field. Both of these magnetic fields are reasonably weak. The gas pressure is dominant over the magnetic pressure in the midplane. But we actually needed to add the vertical magnetic field to drive more stress to drive up our accretion rate, which was too low without that. So this is another parameter that can be played around with. So next we put our simulations, we initialize them in radiation hydrostatic equilibrium. And importantly, we use realistic line opacities. So these line opacities can have an impact on the structure of the disk. So here I'm showing a plot from Zhang et al. 2015. That shows for each line is for a different density, and it shows the opacity as a function of temperature. And you can see, depending on your density, that you get a really significant bump at around 2 × 10⁵ Kelvin. And this is called the iron opacity bump. And because you get this bump, and because somewhere in between the midplane and the photosphere of your AGN disk in these UV optical emitting regions, you're going to have a temperature that's roughly 2 × 10⁵. It's going to have an impact on the structure of your disk. And so here you can actually see it leads to a density inversion in my initial conditions. And this density inversion actually also leads to an entropy inversion. And so you drive convection because you include these line opacities. So that's a source of variability and important to include. Okay, so now the really novel part of these simulations is that I can run it with multiple frequency groups of radiation. So in this case, I'm using 2. So I'm using a low frequency group, which is based on the local disk temperature. So we're in the UV region, so it's in UV. And then I'm also using a high frequency group. So this I am going to be injecting as X-rays. And we model this X-ray light curve as a damped random walk. You know, loosely based on observations, but mostly just something we make up to inject. And so again, right, we have this, we start the run with just this low frequency radiation at local temperature. We inject this X-ray high frequency radiation in our boundary conditions. And then what we can do is we can measure the UV radiation that comes out of the box. And so this is the reprocessing, right? This is the reverberation mapping. X-rays go in, what comes out? And so, and we can compare this to, for example, this B-band light curve from Farrell 9. So that's what we did. So first I'll show you, this is the intrinsic UV light curve from those simulations. So if I run these simulations and I don't inject any X-rays at all, this is the variability we get. And you can see already it does vary. It has variability on different timescales. But now we want to see, we add this injected X-ray light curve. We have a lot of high frequency variability from our X-ray light curve. We want to see what we get out. And so this is what we get. So I'll show them like this to compare them. So first you can see that the reprocessed UV light curve, the one that has the X-rays injected in it in purple, does have some variability that's due to the intrinsic UV, but it does differ. And now I'm actually going to downsample the injected X-ray light curve so you can actually see it a little better. But you can see that there are places where the reprocessed UV does follow the variability from the injected X-rays. So there is some reprocessing happening. I'll zoom in. So now I'm just showing 10 days worth of the light curve. So now I have all the variability that's in the injected X-ray is back. And so you can just compare on these shorter time scales what's happening. And so again, you can see that the intrinsic UV light curve already has high frequency short time scale variability. But there are places where, like, for example, here, kind of that second little peak in the reprocessed UV is clearly from the injected X-ray because it's much smoother in the intrinsic UV. So you are getting some of the signatures from the X-ray in the reprocessed UV, but a lot of it is still just coming from the intrinsic variability of the disk. So now we can look at it more statistically. We can look at the power spectra. So here, right in red, I'm showing the power spectra of the injected X-ray. And then in purple and blue, I'm showing the power spectra for the reprocessed and intrinsic UV. And you can see that they're really similar. So it seems like in our simulations, the X-rays are not fundamentally changing the power spectrum for the reprocessed UV. And then it's also interesting, the lines kind of show I've fit these PSDs with a damped random walk, which is often used to fit used to fit AGN light curves. And we actually find something similar to what observers are finding in terms of our fit for the UV light curves, where at the largest frequencies, the damped random walk is not a good fit. So the shortest time scales, it seems like it drops off steeper than this damped random walk. But we can also use these to measure what the thermal time scale is in the photospheres of our disks, which is useful. So, okay. So here's actually the answer, we think, of why our X-rays are not changing the PSDs of the UV light curve. So you can see here, I'm plotting the injected X-ray light curve in yellow, and then in brown, I'm plotting the emitted UV light curve. And you can see that the emitted UV light curve actually loses power at the largest frequencies. And this is because of the scattering. So I'll actually show you, here is the absorption opacity. And so for the UV, I show it in blue and purple. And for the X-ray, I show it in red. There's just no absorption going on. So the X-ray is very high energy. And as a result, especially in the photosphere and the regions where this reprocessing is going on, the X-rays are just being scattered. There's no absorption opacity. And when that scattering happens, it leads to a smoothing. And that's why we're not seeing this reprocessing like we might expect. So I, again, can't click because, there we go. Okay. All right, we'll see. Right, our summary is that we can use these multi-frequency radiation MHD simulations to simulate reprocessing. There appear to be multiple origins of variability in UV light curves, and that the PSDs of the reflected X-rays are also changed by interactions in the disk. The high frequency variability decreases. And so what we want to do next is, there have been recent observational campaigns, like say with Swift, that find that the X-ray and the UV variability actually isn't super well correlated in their light curves. And so this kind of supports that. But what pretty much everyone finds is that the UV and optical are really well correlated. And so there has to be some reprocessing that's actually going on. And so we suspect that maybe if we do this with UV, which has a lower energy and will have more absorption and less scattering, then you may actually be able to get more reprocessing. So that's the next step. We also really want to be able to write down a physically motivated response function for this reprocessing. And then we also want to kind of do a parameter study with these shearing box simulations to see how this response function or transfer function will change as a function of different parameters. So, okay, I have a little bit of time left, and I want to talk to you about some of the observational work I've been doing, looking for something we're calling a long negative lag. So I just showed you that we have some variability that gets emitted in these light curves that's due to the fluctuations of the disk. So now let's say we have a fluctuation in the outer cooler part of the disk, and it affects the variability of the light curve we observe. So let's say that this fluctuation gets propagated inwards on the inflow time scale and leads to a similar variability in a bluer band from a hotter region of the disk, and then the same variability in an even bluer band from an even hotter region of the disk, right? We should be able to see a long lag in the opposite direction, and I say long because the inflow time scale is long, that is the same sort of kind of reprocessing, but now it comes from fluctuations of the disk being accreted inwards. The problem is in your traditional thin disk model, because H over R is so small, right? It's thin, so the height of the disk is small. Your inflow time scale is hundreds of years. But if you believe that these disks can get puffed up, they can be flared, then if you only increase the aspect ratio of the disk by 1 order of magnitude, because it's squared, you can get down to hundreds of days instead of hundreds of years. And so we actually think we detected one of these in Feral 9, which was the AGN I showed you those light curves for before. So we think we detected a long lag of about minus 70 days from the W2 band to the Z band. And what's really interesting is we can use this to kind of create a theoretical framework for what is this long lag. So we start with the inflow time scale. And now instead of assuming just a normal thin disk with no radial dependence of the height, we say H is proportional to R to some power beta. And if I integrate this inflow time scale and put it in terms of the wavelength, which is how these lags are typically put, then this is what I get. And I think you'll see, if you are familiar with traditional reverberation mapping, you're probably comfortable if I take away the term in the parentheses. This is your standard discontinuum reverberation mapping. But this 7/2 minus 2 beta comes from the fact that the inflow time scale depends on the orbital frequency and this H over R to the minus 2. And so we fit a model to Feral 9 based on the long lags we detected in each wave band. And we actually find that beta is 3 to the 3.6, which is enormous. And so it means that we have this dramatic disk flaring, but not only is the scale height increasing, but the aspect ratio is increasing because H over R goes as 2.6. So, this is our first detection. It may be that instead of disk flaring, we have maybe a collimated outflow, and all of these higher wavelength wavebands are actually coming from the exact same place, and you just have a collimated outflow with a big temperature gradient. But we think this UV detection is pretty robust, and again suggests that you have this puffed up disk in this disk flaring. So I'll just conclude. We want to detect more of these. We want to actually use Vera Rubin to detect more of these. We're working with some data sets already. We're working with more Swift light curves, SDSS, DES, ZTF, and then eventually Vera Rubin. But I hope I've showed you that we can use reverberation mapping, both this long negative lag and more sophisticated models for traditional disk reverberation mapping that are based on, physical simulations, to learn about the physical origin of variability, the vertical profile of the disk, and then eventually we want to use these to learn how these change with different AGN parameters with more long lag detections and more simulations. And the ultimate goal is to use this information to create a new model for AGN disks that's based on observations and these physical simulations. So thank you.
Sorry, as not as a simulator, this may be a stupid question, but in your shearing box simulation, how did you decide looked like your X-ray input was a random walk, but surely there's some level of flux or energy input decision, and that will change your results. And so I don't think I saw you mention that.
No, I didn't. Yeah, that's a good question. So, right, you can see that this PSD, right, the overall power in the X-ray light curve is greater. And so, yeah, so initially we had thought we would put in the same amount of X-ray coming in as UV that's coming out. But we weren't finding that it had a large impact. So we actually upped it, ended up being by a factor of about 8. So the overall power that's coming in is 8 times what's coming out. So I see your shock. Is that, yeah. Yeah.
Observe that the X-rays are 10%, 20% or something, even in low luminosity objects where they're most strong of the UV.
Yeah.
I assume you scale.
Yes. So, I mean, right, like how much ends up in the disc versus how much ends up coming to us. Yeah. So, yeah. Yeah. Right. We're right. So, yeah. So, yeah, I mean, I guess that's another problem that we're injecting more X-rays than you might expect. So, yeah.
Unless you can do it by focusing.
Yeah.
My
Yeah.
actual question.
Yes. Yes.
You're taking this thin wedge where you put a box.
Yeah, shearing box. Yeah.
And calculating everything in that.
Yes.
But the real object has, of course, circular symmetry.
Yes.
And
Yes.
that's going to give some kind of smoothing to your profile.
Absolutely. Yeah.
Is that significant?
Yeah. So we don't know that yet. That's something that, so, right, at the these simulations are expensive. Doing multi-band radiation is expensive.
But you can
So,
estimate the radius.
yes,
and you can estimate
right. How get blurred. Yeah. Well, actually, we probably could do that. So, yeah. Because, right, ultimately, we'd like to do a more global simulation, right, where we can actually find that. But yes, so, right, we do suspect some of this high frequency variability will go away. Yeah.
We have time for one last question. If not, let's thank our speaker again.
Thank you.
I'm sure Emmy has some free spot still, if
Yeah.
you want to meet with her.
Definitely.
So go and find her and chat.
What am I doing?
And moving forward, our next speaker is Alessandro Peca. He's a last year graduate student at the University of Miami, working with Nico Capelluti. Alessandro started working on AGN surveys when he was just a master's student in Bologna in Italy. And he consequently won a fellowship. After that, he moved to Miami to work with on data from Stripe 82X and on big data regarding AGN. And today is going to be the talk about unveiling the dark side of the universe, harnessing the power of big data to reveal a hidden and heavily obscure AGN population. Alessandro, field is yours.
All right. Thank you for the nice introduction and for having me today. And thank you, Rafael, for inviting me. So today I'm going to show you what I did in what I'm still doing in my PhD. And my name is Alessandro Peca. My advisor is Nico Capelluti, but as you can see here, many people collaborated with us during the last year. So I'm going to show you how we can use big data and, in general, large data sets to unveil obscure AGNs. So I will start showing you why there is a problem with obscured AGNs, or at least why we think there is a problem. And then I'm going to show you 2 different solutions to tackle this problem. So obscured AGN. When we talk about obscured AGN, we need to talk also about the cosmic X-ray background, as you can see here in this plot. So we believe that this cosmic X-ray background is produced by unresolved, extremely obscure AGN in the universe. And as you can see, all the colored lines in the plot, except for the green dotted line, which is the contribution from galaxy, all the other lines are the contribution of AGN's populations with different level of absorptions. And in particular, I want you to focus on the red line, which show you the contribution of Compton-thick AGNs. Compton-thick means AGNs with column density larger than 10 to the 24 centimeters to the -2. So what we can do is to try to reproduce the X-ray background using population synthesis models, which basically means put together some simulations and see how many AGNs we need to reproduce the CXB. So we can infer the number of these obscure sources, but the point is that, do we see them? And the answer is not very well. So to show you that we have a real problem here, this is just an example from Torres Alba 21 and Sengupta 23. They use SwiftBat, which is a very nice telescope if you want to be almost unbiased against obscuration. And this is because it's able to collect X-ray photons at energies larger than 100 keV. So we can say that, at least in the local universe, is almost unbiased against NH. And these authors, for very low redshift, up to 0.05, they found an obscure Compton-thick fraction of 80%. However, if you use some population synthesis model, you can see that the predicted Compton-thick fraction is below 20 and 50%. And for example, if you use the Anana 19 model and you apply observational biases and completeness biases to this work, you can get an expected Compton-thick fraction with between 27 and 38%. So the difference is huge. And even if you use the Ueda 14 model that predicts less obscuration, prediction and observation still do not match. Moreover, we know from several studies that obscuration in galaxies increases with redshift, and heavily obscured AGN are faint. And because they are difficult to detect, with also the effect of the higher obscuration at high redshift, we expect this discrepancy to be much higher at the beginning of the universe. So how we can solve this issue? Solution A, using large area X-ray surveys. So here you can see the sensitivity area plot on the left, and on the right, the so-called wedding cake diagram. And they basically show you the same thing. So if you look at the plot on the left, you can see that the perfect X-ray telescope doesn't exist, because you cannot go at large area and low fluxes. So we need to choose between deep pensive beam surveys and large but shallow surveys. So first of all, we have many works that used deep surveys, and it's true that when we talk about obscuration, we are talking about faint objects, so you may say that we need deep surveys. However, if you take an X-ray luminosity function like this one, you can see that at high luminosity, these objects are rare. And because they are rare, you need to sample large volume of the universe to get them. And the reason we want them is that high luminosity and high NH AGN seem to be in a key phase of AGN evolution. So it's important to find and characterize them. So we started using the STRIPE-2X, which is 31 square degrees XMM Newton and Chandra survey. So it's a large area survey in which we have also redshift completeness around 100%, which is fundamental if you want to do a detailed analysis of AGNs. And we also have multi-band coverage over 25 bands, meaning that we have high quality photos D and very important complementary information. And then we have numbers, because we have more than 6,000 X-ray sources, of which 1,500 are hard band detected, which is always good if you want to look for obscuration. So this is just a scheme of what we did. We started from the La Massa 16 catalog. We made some redshift and X-ray spectral quality cuts, meaning that we selected only objects with spectroscopic or high quality photometric redshifts. And then we made a lot of simulations to determine the minimum number of photons that you need to get a reliable fit. After these cuts, we got a final sample of around 3,000 AGNs. And this is one of the results. So here you can see the intrinsic X-ray luminosity is a function of redshift, and you can see how Strip82X samples very well the high luminosity part of this plot, and we share the area with other large surveys like XMM, XXL. However, when I was looking at this plot, and for some reason, I'm really, really obsessed with obscuration. I was wondering how many obscured AGN are we missing here below that black line, which basically tells you that we cannot get the lower luminosity ones and the most obscure ones because our survey is shallow. And to answer this question, we can answer this question making some simulations. So here you can see a representation of a perfect telescope. So you see NH versus redshift, while on the z-axis, you see the percentage of AGNs that you can get from an observation. So of course, if you have a perfect telescope, you get AGNs at all the NHs, all redshift, and all the luminosities. However, what we did is to apply observational limits and observational biases to our simulations to get basically a real telescope. And then this is what we get. So we have a percentage of object as a function of physical parameters. Here I'm just showing you NH versus redshift, but we did it also for luminosity. And basically it's telling you for each set of parameter, the percentage of objects that we are getting or we are losing in our observations. So without assuming any luminosity function, since those are percentages, we can just apply the percentages to what we see. And what we see here is just an example in which I show you our distribution of NH, LX, and photon index. And the results of that is intrinsic distribution. And when I say intrinsic distributions, I mean, at least if this procedure works, we look at intrinsic number of AGNs, meaning that we are looking also at what we don't see using observations. So the first thing we did is to compute the Compton-Tin fraction. Compton-Tin means that we have obscured AGN with an H between 10^22 and 10^24 centimeters to the -2. And we trace the obscured fraction evolution as a function of redshift for all these luminosity beams. And you can say that it's clear that obscured AGN increases with redshifts at all the luminosities, but I want you to focus on the green plot on the right. We are pretty proud of it because we were able to put constraint in the high luminosity regime of AGNs. You can flip this plot. So this is again the obscured fraction as a function, this time of luminosity for different redshift beams. And you can see how the obscuration decreases when luminosity increases. But then we did, now I don't have the time to go into the details, but we did much more. We computed obscured and unobscured luminosity function up to redshift 4. Everything is on our paper, so if you want them, just go there. We also computed the black hole accretion density evolution, in which we found hints that the Compton-Peak fraction of objects we found hints that we have more obscured, highly obscured objects than previously thought. Now, the next step is called Strip82XL, for which we won a Chandra archival proposal. So the data I showed you before are up to 2016. So from that time to today, we discovered a lot of new archival XMM and Chandra observations. And so we decided to increase our number of AGNs by creating this new Strip82XL surveys, which is 2 times deeper in some overlapping regions, and it reaches a total area of around 55 square degrees of hard X-rays. And our expectations are that we can improve previous studies by going to higher redshift, high luminosity, and going to the Compton-Peak regime. So now some preliminary results on this survey. So what we did is we went to the 4XMM and Chandra source catalogs to check all the detected sources. And right now we have a total number of more than 23K AGNs. And as you can see on the histogram here, you can see how we have many, many more objects right now and how we can reach lower fluxes in which we expect to find very obscure sources. So I already did the multi-wavelength counterpart association. We have 92% of sources with multi-wavelength counterparts, and we did the match with Lyra, which is a maximum likelihood estimator that I wrote, and is very nice. But now let's go to solution B. So I show you how using large area X-ray surveys is useful to improve our understanding of obscuration in AGN. However, we can do more than that. What about using all the discovered AGN that are available in the literature? So this is called AGN database, or AGNDB, and it aims to be the repository of all the discovered AGN at all the wavelengths, at all the redshifts. And you can find in this database information on redshift, classification, photometry, images, SEDs, and in the future also spectroscopy. So how we did that? How you can build such a huge database? So we stored together all the catalogs in which there are AGNs, and then we made a pipeline. Our pipeline is able to unify all the units from all the catalogs, is able to deal with all the catalogs formats, and is able to merge overlapping catalogs using Lyra, and it can ingest new catalogs with a semi-automatic procedure. At the end of this pipeline, you can get a single beautiful master catalog in which you can make queries, you can download the results, and you have access to images, SEDs, and spectra in the future. So if you take all the sources that we have, all the AGNs that we have, we are talking about 7.5 million unique AGNs, and you put them in this projection. This is a density plot. So where you see yellowish color, it means that we have more AGNs. And all those stripes, you can clearly see the shape of the SDSS there. So all those geometrical figures are because of surveys. And these are just some of the numbers that we have. We have a high redshift completeness. We have 66 magnitude and flux bands, a lot of X-ray, infrared, optical, radio, and far infrared information. So why we build that database? Well, because basically we want to do the same using the largest repository of AGNs, right? I told you that we need numbers, we need statistics. So why don't put all the AGNs together? So AGNDB is potentially the best tool to study high NH, high redshift AGN population, especially talking about Compton-Tick AGNs. Now, let me go a little bit out of topic and make some advertisements. So we are doing many projects with the AGNDB. So I told you about doing an X-ray spectral analysis for the entire catalog. We are going to include catalogs without solid classification, meaning that since we have only solid classified AGN in the database, we can take all the other catalogs, match them together to improve our photometry completeness. Then we are performing SED fitting using Sigali over the entire catalog to get AGN and nose galaxy properties. Then I want to build a multi-band and monometric luminosity function. This is actually the project that I'm proposing for postdocs. So if you like it, here. And then we have a very nice misclassification project. So we believe from some preliminary machine learning tests that there are some misclassified AGN in our database, and which means that they are also in other catalogs. And actually nobody is working on the project. So if you're interested, just let me know. And then we have collaborations with Yale in which students and postdocs are working on the morphological classification of host galaxies, and other students that are computing black hole masses for as much AGN as they can. So let's go to summary and conclusions. So I show you how we need more obscure AGN than those observed to reproduce the X-ray background. So we have this discrepancy between observations and models that we need to solve. We tried to solve this issue with the StripedT2X, and we found some hints by looking at the black hole accretion density. I didn't show it to you, that the Nano 19 model, which is one of the models that predicts more obscuration than the other, is the one that works best, meaning that this discrepancy is there and is very high. To solve this discrepancy, we tried with different approaches using wide X-ray surveys like the StripedT2X and the StripedT2XL. And then we tried with AGNDB. So we tried to put all the AGNs with all the multi-wavelength information together. And I want to conclude just to say that big data repositories and large surveys in general open a wide range of new opportunities. It's not only about obscure AGN fraction, but it's also about luminosity function, host galaxy properties, black hole masses, mini classification, and any other project you can think of. Thank you for your attention. And I'm happy to take any questions.
Any questions? Thanks.
Hi, great talk. So this large fraction of conflict AGN, have you thought about implications for the average radiative efficiency that's required to match black hole masses with the Sultan argument?
Yeah, that's a very good point. So we thought about that. And so what people usually do is just to assume an efficiency, right? Which is usually 0.1 or whatever. We didn't try to put other values other than that. But the point is that when you compare models, I mean, if you use the same efficiency for all of them and you find discrepancy, you can see that there is a huge difference between the Compton-Tick predicted fractions. And so it should, I mean, if you change the efficiency, that discrepancy should remain in place. I mean, I think, of course, if there are huge variations, that may not be true, but yeah.
Hello. So you have a prediction, or you have a model which includes the total NH, the redshift, and the luminosity of your AGN.
Correct.
So you can, from that, construct an expected infrared luminosity function and compare it with Y's or something like that. Because this radiation has to come out somewhere, probably in the mid-infrared.
That is correct. And this is actually, so if I show you some of my applications for postdoc, this is what we want to do. So we didn't do that yet, but the main idea, since we have this large repository, we want to build a bolometric or even a multiband more luminosity functions. And then we can make comparisons, predictions, and so on and so forth.
Just one slide.
Okay, we have a question online, so you can speak up. Dan, I saw you.
Yeah, I raised my hand. I can't hear falling on me. But my question is, how do you define an AGN? And I'm asking because the integrated ground depends sensibly on the.
We have a sort of lag. Can you speak very slowly so we can work around that? Can you repeat your question slower, please?
No, I didn't finish asking my question. Can you hear me?
Yeah, but there is a bit of a lag, and so if you speak faster, your words sort of overlap with each other. Can you speak slower, please?
I'm going to put something in the chat to read.
Excellent, thanks. Do we have any other questions in the meantime?
Oh, okay, we got his question.
Okay.
So he says, how do you define an AGN? I ask because the integrated background depends sensitively on the low luminosity cutoff, and maybe you don't count those as AGN.
Yes. So if the question is about our AGN database, that is a very good point. Right now, we define an AGN, an object that other people defined as AGN. This is why we have this misclassification project that we want to do, because right now the caveat is that if somebody published a catalog saying that an object is an AGN, for us is an AGN. But I will say that, so for example, we have more spectroscopic redshift than photometric redshifts. And this is because we tried to put in our database only objects in which we trust the classifications. So for example, many objects, high redshift objects in which the classifications come from, like SED fitting, we just try to avoid to include them. But yeah, this is a caveat that we have.
Okay, so let's thank our speakers again. I can see some nice script in the background, so please go ahead. And see you next week, I guess.